4.2 is a really nice extension of 4.1. In fact, I actually kind of already taught 4.2 at the end of 4.1. So hopefully this feels a little bit like review. The first thing we're going to start with is just putting down on paper the official number of zeros that you can get for a polynomial function. So this is really important in the days coming up. We are going to be solving polynomial equations and finding all the zeros. And so it's good to know how many you can get. So the rule is that whatever the degree is of the polynomial, that's the most number of real zeros you can get. So I say the most because, you know, even if we look at something like this, where the leading term is negative x to the 6, which means this is a 6th degree equation, even though you can have a maximum number of 6 real zeros or x-intercepts, you're not necessarily going to have all 6. You know, maybe 2 of them are the same, right? A multiplicity of 2. And so on your graph, you're only going to see 5. Or maybe some of them coming up soon are going to be imaginary. And so you won't see them on the x-axis. So we say the maximum number of real zeros for a 6th degree equation is 6. And then turning points, what that means is relative max and mins. So if I have a graph that has, let's say, 6 x-intercepts, 1, 2, 3, 4, 5, 6. So this is the max you could have. So all of them would have to be crossing the x-axis. So we'll just go 1, 2, 2, 2, 2. Okay. So we look at the number of max and mins. So here's 1, here's 2, here's 3, here's 4, and here's 5. In fact, there's a rule. You always have a maximum of n minus 1 turning points. In other words, if it's a 6th degree, then you can have 5 turning points. Okay, pause the video. Figure out which is your leading term of this polynomial expression or function, and then determine the maximum number of real zeros or x-intercepts and the maximum number of turning points. So hopefully you found that there is 4, because this is a 4th degree or quartic function. And so then you have at most 3 turning points. All right, so now what we're going to do is what we did at the end of 4.1, which is sketch polynomials. And again, I sketch, okay? Your textbook, the instructions will say graph. I'm not calling these a graph because we're not going to find all the representative points to get a perfect shape. I'm calling these a sketch because when we use these, which is going to be for inequalities, I'm not going to care how high or how low your graph goes. I'm just going to care that they go above the x-axis or below the x-axis. If I wanted you to graph, I would use graphing technology because these ones have so much to them that we would need so many points to make these look accurate. So I'm going to call these sketching. When you do your questions in the textbook, keep in mind that even if it says graph, I want you to sketch. So the steps to sketching are as follows. Step number 1 is you're going to use the leading term test to determine the end behavior. So what I'm looking at, is it even or is it odd? If it's even, is it even positive or is it even negative? If it's even positive, it's a parabola opening up, right? That's your guide. So it starts in quadrant 2 and it ends in quadrant 1. If it's even negative, you're using a parabola opening down as your guide. So it's starting in quadrant 3 and ending in quadrant 4. If it's an odd positive, it's starting in quadrant 3 and ending in quadrant 4. Think of a line with a positive slope, right? It's going to start bottom left and reach up to the right. And if it's odd negative, you're thinking of a line with a negative slope. So it starts in quadrant 2 and ends in quadrant 4. Sorry, I put 4 here. I meant 1. Sorry. Okay, so your even graph, positive starts in 2, ends in 1. Odd positive starts in 3, ends in 1. Even negative starts in 3 and ends in 4. Odd negative starts in 2 and ends in 4. So they have the same end. Then what you do, once you know your end behavior, is you're going to find your zeros. You're going to find the zeros of your function by solving when f of x is equal to 0. Then we're going to use our multiplicity rules for the x-intercepts to sketch the curve. Or I'm going to teach you an alternate method of using the x-intercepts to divide the x-axis into intervals. So this will be the interval method. And you're going to choose test points to decide whether your graph is above or below. That's really the only 3 steps you need. You know, optionally, you can find the Y-intercept. I don't often, only because the Y-intercept is often not something that will fit on a grid. So you could use the y-intercept to check and see if you're in the right section, or if I was trying to identify the graph of something from an equation, I would use the y-intercept to say which one it is. But I generally don't use it for sketching, and I generally don't find other points to sketch a graph because we're sketching, we're not graphing. Okay, so let's do it. So step number 1 is to use your leading term test to determine your end behavior. So I have to figure out the degree of this polynomial. So this is written as a product of linear factors. So I have to multiply the x's together to find out the degree. So I have 2, I have 3, and I have another 1. So this is going to be a 6th degree equation, which makes it even. Okay. Also means that there's going to be a maximum number of 6 x-intercepts, or 5 turning points. Now, to figure out if it's positive or negative, I'm looking at that leading term. Since it's negative, I know that it's going to start in quadrant 3 and end in quadrant 4. Step number 2 is I'm going to find what the zeros are. So I'm going to use the product of zero factors. Is that what it's called in this course? I can't remember. Anyway, you're going to be looking at what makes each factor equal to 0. So you've got x equals 0. You've got x equals 4, and you've got x equals negative 3. So what makes each of these factors equal to 0? And then I like to write these in numerical order. So I'm going to write my x-intercepts as negative 3, 0, 4, because it just helps me transfer them onto the grid. Instead of trying to look, okay, what do I do at this one? Now what do I do at this one? And then I write my multiplicities. So the multiplicity of my x-intercept negative 3 is 1. The x-intercept, or the multiplicity of my x-intercept 0 is 2, because it's squared. And the multiplicity of my x-intercept 4 is 3. What does that mean? Well, my options are pass through, touch, or flatten. So I'm looking at the degree or the multiplicity to tell me that. When it's a multiplicity of 1, I'm thinking of a linear graph, so it passes through or crosses the x-axis. When it's a multiplicity of 2, I know that this is an even degree, which means I'm tangent to the x-axis, which means you do not cross through. So I'm going to say that I just touch at my x-intercept of 0. And then when the multiplicity is 3, I'm thinking of an x cubed graph. And an x cubed graph has that little flattening that happens. So it's going to flatten and cross through the x-axis. Then what I'm going to do is I'm going to put those x-intercepts onto my grid. So I've got x equals negative 3, x equals 0, and x equals 4. And I'm going to use my leading term test and my behavior to then sketch. So I'm going to start in quadrant 3, and I'm going to do the following. I'm going to cross, I'm going to touch, and I'm going to flatten and cross. Meaning I'm going to cross through, then I'm going to touch, come back up, and then the next time I go to this x-intercept, it's going to cross through, but it's going to do a little flattening. And that's my sketch. It's a sketch. Okay. If I go to look at this in Desmos, maybe this goes higher, maybe this goes higher, maybe this goes lower. It does not matter to me. What matters to me in the end is that you can see that if I were to take this x-axis and sort of look at it just a bit simpler, I have an x-intercept at negative 3, I have an x-intercept at 0, I have an x-intercept at 4. The graph is below the x-axis, it's above the x-axis, it's above the x-axis, and it's below the x-axis. That's what's going to be important by the end of this chapter, because the end of the chapter is going to be inequalities. When is it greater than 0? When is it less than 0? Okay, moving on. If the whole multiplicity thing just boggles your mind, you are more than welcome to use the interval method, and the textbook uses this interval method. The interval method works by using no knowledge. In other words, you don't have to know that this is an even graph. You don't have to know it's a negative graph. You don't have to know end behavior. You don't have to know multiplicities. You just have to know the x-intercepts. So the x-intercepts haven't changed. They're still 0, 4, and negative 3. Okay, so I could even put those on. Negative 3, 0, and 4. Okay, but now instead of saying, okay, I'm going to start in quadrant 3 and end in quadrant 4, I'm going to cross, I'm going to touch, I'm going to flatten, we're going to test. We're going to test a point in each interval. So there's one interval between negative infinity and negative 3, so this is the first interval. There's another interval here between negative 3 and 0. There's another interval here between 0 and 4. And then lastly, there's an interval here, which is between 4 and infinity. And what we do is we pick a number, pick an x value that's in those intervals, test it into the equation, and determine the function value. So something between negative 3 and negative infinity would be negative 4. Something between -3 and 0 would be -1. Something between 0 and 4 would be 1. Something between 4 and infinity would be 5. And we plug these in for x and solve for y. So technically this would give us points, but as you're going to see, the points they give us, I'm never going to graph because they're crazy. But what you do is you now plug those in. So I'm going to plug in x is -4. I get -3 times -4 squared times -4 minus 4 cubed times -4 plus 3. And you're going to type it into your calculator. So do practice this. I'm going to type in -3 times -4 squared. Make sure when you type that, when you hit -4 squared, make sure your calculator puts brackets around the -4. If it doesn't, you will need to put the brackets in there because it's -4 squared, not 4 squared. Then I'm going to go, this is -8 cubed, and then times -1. Sweet. Okay, so that gives me -24,576. Sweet. Never putting that on a graph. But what does that tell me? That tells me that when the x value is -4, right, something to the left of this x-intercept, the y values are negative, which means that the graph will be below the x-axis. And then we keep going. Now we're going to plug in -3. I get -3 times -3 squared times -3 minus 4 cubed times -3 plus 3. Oh, sorry, I can't plug in -3. Stop me. It has to be something in the interval. I told you that we were going to plug in -1. So let's just put that in. It's been a long day. There we go. Sorry about that. Okay, so we're picking -1. So it's going to be -3 times -1 squared times -1 minus 4 cubed times -1 plus 3. All right, let's plug that in. So I get -3 times -1 squared times -5 cubed, or I could plug in -1 minus 4, times 2, which gives me positive 750. Again, I don't really care that it's 750 because I'm never going to put that on a grid, but it is positive. So when I have an x value between 0 and -3, the y value comes out positive. So my graph will be above the x-axis. All right, pause the video, and I want you to plug in when x is 1 and when x is 5. All right, so hopefully you did pause the video. When you plug in x is 1, hopefully you got 324, which again is positive, and the graph will be above the x-axis. When you plug in x is 5, you should get -600 for y, which is negative, so the graph will be below. So how do I use this? Well, now I know that when I'm approaching this x-intercept from this interval, my y values are negative, so I'm going to start below the x-axis. Then between the next two x-intercepts, or these two x-intercepts, my graph will be above. Between the next two x-intercepts, my graph's above again, which means I have to turn around. And then my fourth interval, which is to the right of 4, it goes below, so I have to cross through again. So this is the sketch that this method would give me. And what you'll notice is the biggest thing missing is that your graph, you'll never know that it flattens here. And that's okay. Okay, because again, the flattening out won't affect my inequality. It won't affect whether I'm above or below the x-axis. It's a shape thing. For me, I like it because it's something that I know. I know that the graph does that. So if I was to then put this in Desmos, I'd be like, well, look, there's a flattening out at this x-intercept. It's more information. But for where we're going with this, it won't matter. So I will expect that if you use multiplicities, I want to see some kind of work. You know, I want to see something like this flattening out. Maybe you write out your x-intercepts and tell me the multiplicities or what their behavior is going to be. If you're doing this method, I want to see, you don't have to do this chart. I would love it if you did something like this, right? And then when you plug them in, I love to see that the graph is below, the graph is above, the graph is above, the graph is below. Something along those lines, showing where the graph would be. But you don't have to show me actually plugging everything in either. All right, so now that I've taught you the method, what I'd love it is if you're feeling confident, pause the video and give this one a go. If you're not feeling confident, don't pause the video and listen to me walk through it. So here we go. Step number 1. I'm going to do this using multiplicities because I find that's the one that takes kind of the most coaching to get used to. If you're using intervals, I find people are usually good to go. But regardless, it is good to know that this is an even degree because it's a fourth degree. So this is a fourth degree equation, right? 1, 2, 3, 4, which is even. Because the leading term is a 1, that's positive. So since it's even positive, I know it's going to start in quadrant 2 and end in quadrant 1. So even if you're using the interval method, you can still figure that out. Maybe that means that you don't have to plug in something in these two intervals because you're like, I know the end behavior. I know this one started in 3 and ended in 4. I know it's going to go negative to negative. This one I know is starting in quadrant 2 and ending in quadrant 1. It will be positive. It'll be positive, right? You can use kind of both methods to help you. And then what I'm going to do is figure out the x-intercepts. Again, this is the same for both methods. I have an x-intercept at -1, I have an x-intercept at 2, and I have an x-intercept at 4. I could put those on my grid right now too if I want. Okay, now I have to figure out what's going to happen. Well, I can do the interval method, or I can use multiplicity. So this one has a multiplicity of 1, which means your graph will cross the x-axis. The x-intercept of 2 has a multiplicity of 2, which means you will just touch the x-axis. X equals 4 has a multiplicity of 1. So again, you will just cross the x-axis. So if I was to do this, I'm going to start in quadrant 2. If I do it right, I'll end in quadrant 1. So I don't really have control over that once I start graphing. But what I'm going to do is I'm going to start in quadrant 2. I'm going to cross through. I'm going to just touch. And then I'm going to cross through again. That was a bit wonky, but you know what I mean. And that's it. If I was doing this from an interval perspective, I would have an x-intercept at -1, an x-intercept at 2, and an x-intercept at 4. I would test a point like -2. I would test a point like 0. I would test a point like 3, and I would test a point like 5. If I plug those in, I would realize the graph was positive for the -2. At 0, the graph is negative. At 3, the graph is negative. And at 5, the graph is positive. And that will also give me this behavior. All right, next one. Next one, the difference here is that my equation is not written as a product of linear factors, so it's not as easy to see what my x-intercepts are. But I can figure out my leading term. So my leading term is -x³, okay, which makes this an odd graph. So let's say this is 3rd degree. Maximum number of 3 x-intercepts, which is odd, and it's negative. So I know that this graph is going to start in 2 and end in 4. Now I have to figure out what the x-intercepts are. They are not clear, right? This is not factored. I can't use that principle of zero products, right? Instead, I have to make it. So I'm going to set it equal to 0 to solve. I'm going to say 0 equals -x³ plus 2x squared plus 4x minus 8. Now, we're still in 4.2. This is your last day that you get to say, hey, this is factorable. After today, so the next lecture, you are not necessarily going to be able to factor everything that asks you for zeros. You'll use other skills, but for this one, I guarantee you can factor. So how many terms are there? 1, 2, 3, 4. That means that I can factor this by grouping. Here's group 1, here's group 2. Out of the first group, I'm going to take the sign of the first term, and I'm going to factor out -x². If I factor out -x², in the bracket, I will be left with x minus 2. Out of here, I can pull out a +4. And if I've done this correctly, I get that same bracket, x minus 2. Then I'm going to factor by using greatest common factor. So I have 2 terms. My greatest common factor is x minus 2. And I'd be left with -x² plus 4. Now, the whole goal of this is to find the zeros, not to fully factor. So you have 2 choices at this point. You could keep factoring to find the zeros, or you could solve. So I'm going to look at this, and I'm going to say, hey, you know what? I can see a difference of squares here, almost. I'm going to keep factoring. I'm going to factor out -1 from both of these terms. I'm going to write it out front. I've got -1 times x minus 2 times x² minus 4. Then I can see the difference of squares. So I have -1 times x minus 2. And to factor difference of squares, it's x minus 2 and x plus 2. Sweet. Now, hopefully what you recognize is that there are two identical x-intercepts. In other words, this x-intercept at 2 will have a multiplicity of 2. And maybe it would be easier to see by writing, hey, this is x minus 2 all squared times x plus 2. So this is one way to show that the x-intercepts are 2 and negative 2. I'm just going to point out that we could have stopped here. So that's one way you can fully factor. Option number 2, so this is option number 1. Option number 2 is that when you got to that place where you had 0 equals x minus 2 times negative x squared plus 4, what we're really trying to do is solve for the zeros. And so as soon as I get to a place that I can solve, I don't have to keep factoring. What I mean by that is I could say, hey, what makes this factor equal to 0? So what makes x minus 2 equal to 0? Oh, when x is 2. Okay, that's easy. And then you do the same thing here. What makes negative x squared plus 4 equal to 0? And then you solve. So I'm going to add x squared to each side. And then I'm going to take the square root. When I take the square root, I have to remember plus or minus the square root of 4. And I get x equals plus or minus 2. Sorry, talking and writing, not my strong part. So what you would notice with this one is that I got the x-intercepts of 2, 2, and negative 2. And that'll show me again that that x-intercept of 2 has a multiplicity of 2 because it showed up twice. So if I was doing this, I have two x-intercepts, negative 2 and 2. The difference is the x-intercept of negative 2 has a multiplicity of 1. It happened once. And the x-intercept of 2 has a multiplicity of 2. It happened twice. So whether you see it from the factored form or whether when you solve you come up with two x-intercepts that are both 2, that's what shows you the multiplicity. So now I'm going to sketch. I'm going to put those x-intercepts on my grid, negative 2 and 2. I'm going to say that the one with a multiplicity of 1 crosses the x-axis, and the one with a multiplicity of 2 touches the x-axis. So where do I start? I'm going to start in quadrant 2. So I'm going to start in quadrant 2. It's going to end in quadrant 4 for me, as long as I cross and then touch. So I'm going to start here. I'm going to cross the first x-axis, and then I'm going to touch the x-axis. And that's my sketch. If you wanted to do the intervals again, you just break it up. Right? You break up your x-axis into negative 2 and 2, and you test points. I'm going to try negative 3. I'm going to try 0. I'm going to try 3. If you do that, it should come out that your y values are positive, negative, negative. That shows you that you just touch at that x-intercept of 2. All right, last thing. So this last thing takes a totally different turn. It's a very specific theorem. So when you're doing your homework, you're going to come across a question and it's going to say, use the intermediate value theorem. Okay, very specific. The intermediate value theorem says, if you plug in values of x, if the y values, so the output, ends up being opposite signs, then there had to be a 0 between those two x values. What I mean by that is that if we check an x value of something like negative 4 and we check an x value of something like negative 1, if it goes from negative to positive, you had to go through the x-axis to get there. Or if it goes from positive to negative, you had to go through the x-axis to get there. If you do this and you plug in x is negative 4 and you plug in x is negative 1, and the signs don't change, so if it stays negative or it stays positive, then we cannot determine if there is for sure a 0. So that's what we're checking. Is there a 0 between two x values? So in other words, would there be an x-intercept between two given x values? And if the y values change, then there was. You had to cross the x-axis. If it doesn't, well, there might be. Okay, so let's try it. So this one says, is there a 0, at least one 0, between an a value of negative 4 and a b value of negative 1? So what I mean by that is plug in an x value of negative 4 and plug in an x value of negative 1. So plugging in an x value of negative 4, we get negative 4 cubed plus negative 4 squared minus 8 times negative 4. That would give me negative 4 cubed plus 4 squared is 16 plus 32. Gives me negative 16. Okay, so this is a negative y value. So at negative 4, we know that the y value is negative. Now we're going to plug in x is negative 1. So negative 1 cubed plus negative 1 squared minus 8 times negative 1 gives me negative 1 plus 8, which is 8. So at x is negative 1, my y value came out positive. Since there was a sign change, that means therefore there is, I can't write, there is at least one real 0. If it had come out that there wasn't a sign change, then you would say, I cannot determine this. There might be, there might not be. So you would just say, I cannot, the intermediate value theorem cannot be used to determine. All right, good luck.